Alright, so in this tutorial we're going to be looking at an introduction to acids and bases, as well as some definitions about acids and bases that you'll need to be aware of. We're going to focus on titrations and pH later on, but we're going to start with just sort of some basics, hopefully things that you're already pretty aware of. So if we're going to look at some things that we already know about acids, many are corrosive, many are poisonous. You want to think like battery acid, any sort of like citrus, right? That's where we get that sour taste. Think citrus. Okay. They're going to react with metals to form hydrogen gas. We looked at this when I put magnesium metal and hydrochloric acid together at the beginning of the year. We got a rapid production of hydrogen gas and magnesium chloride in our test tube. Okay, it's going to change the color of your indicators to a red, a pink, or a yellow. I like to call those the warm colors. They're really good at conducting electricity, which is why we call them electrolytes. And if they're going to react with a base, you're going to get water and a salt, which, if you remember, was that last category of chemical reactions that we talked about in chapter 8 that I said we would come back to. We're coming back to it now. And so you're always going to get water, you're always going to get a salt. What we also want to remember is that we do have strong versus weak acids and bases. It has to do with dissociation, which we will talk about a little bit more. Sorry, I totally spelled that wrong. We'll talk about that a little bit more as we go along, but really we're talking about the breaking up of different breaking up your hydrogen, your chlorine, breaking up your hydrogen, your NO3. So these are your 6 strong acids that you need to be aware of. You should memorize them. Okay. Every other acid is going to be weak, meaning that we're not going to get full dissociation. And again, we're going to talk more about what dissociation means. When we talk about bases, I often think that people think that bases aren't necessarily as harmful or as dangerous as acids, when in reality that's not true. They're still corrosive, they're still poisonous. They tend to have a bitter taste, but we never want to taste this in class, obviously. They tend to feel slippery between your fingers, so you want to think soap. Any sort of soap is going to be a base. They tend to turn your indicators the cooler colors, your blues, your greens, your purples. Again, they're going to react with an acid to form water and a salt. They as well are also good electrolytes, but we don't want to discount them as being potentially less dangerous than acids, because they're not. They are equally as dangerous. They are equally as harmful. They can burn you. They can do all of that. So we just want to make sure that we understand that as well. And again, we do have strong versus weak bases as well. Again, full versus partial dissociation. So you want to remember these 8 bases. You're going to notice they all end in OH, or hydroxide, which is one of our polyatomic ions that we should know. So you should have all of these memorized, or at least a place where you can reference them really. Now we're going to be focusing on 2 different definitions of kind of how do we define an acid, how do we define a base, what does it mean to be an acid, what does it mean to be a base. So we are going to be taking a look at the Arrhenius and the Bronsted-Lowry definition. The Arrhenius is quite simple. Bronsted-Lowry is a little bit more complicated. Arrhenius tends to be a little bit more incomplete, which is why the Bronsted-Lowry came in place. So an Arrhenius acid, this is any substance that's going to ionize, again, break up into its ions to produce a hydrogen ion or an H3O plus ion. This is what we call hydronium. Hydronium. Okay, you want to be aware of that. H3O plus is the same as H plus. Okay, so we want to remember that ionization is not the same as dissociation. These are things that are becoming ions because they react with water molecule. Dissociation happens when something dissolves, but there's not a direct reaction with water. So with an Arrhenius acid, it's anything that's going to ionize, or anything that when it goes into water is going to break up and leave a hydrogen ion behind. Okay. And again, when you have a strong acid in a solution, you're going to have complete dissociation, something like HCl or HNO3, as you can see in these 2 examples here, right? And then you also have Your weak, right here, this is acetic acid. Acetic acid is vinegar, okay? So they're not going to get full dissociation there. You can tell by the double arrow. This double arrow tells me that the reaction can go in either direction, okay? Whereas up here, you're just getting that single arrow, meaning that it's going all the way to complete, okay? An Arrhenius base is going to be anything that ionizes or dissociates to form hydroxide ions. Again, if you have a strong base, these are going to be like things such as LiOH, NaOH that you can see up here, again indicated by that single arrow going to completion. If you have a weak base, you're going to get that double arrow, something like ZnOH2, or if we look at this example here for AgOH, if you have AgOH, we know that it's weak, so it's going to be a double arrow, and you're going to get Ag plus OH minus. It's going to break up into its two parts. Now, what you want to keep in mind is that the Arrhenius definition doesn't take into account all things that act like an acid or all things that act like a base. Something like NH3 is definitely a base, but it doesn't form hydroxide ions in solution. The hydroxide ion doesn't come from NH3 itself, it comes from another place. So even though they exist in the solution, since they're not coming from the NH3 molecule itself, technically under that definition, it doesn't count as a base. So that's where the Bronsted-Lowry definition comes in, because it's a little bit more inclusive for things like NH3, which is most definitely a base, even though it doesn't give off those hydroxide ions. So if we're looking at a Bronsted-Lowry acid, these are anything that's going to donate a proton. So when you put it in solution, it's going to give away a proton. And a base is going to be anything that takes in that proton. Okay, so this is going to include everything that an Arrhenius acid or base plus more, right? So you're going to get what we call acid and base conjugate pairs. Okay, so when we look at what's going to be a proton donor and a proton acceptor, you want to look for something that's going to start with an H. If you don't have anything that starts with an H, then that's probably going to end up being the base. Now, in this case, you've got water and HCl. So HCl starts with an H, okay, so it's going to be our acid. So that's going to donate your hydrogen ion to water, creating H3O plus, and then leaving the hydrochloric acid as just a Cl, okay? And again, we're still working with that one-way arrow. If you have something like NH3, doesn't start with an H, but water starts with an H, okay? So water is going to donate its hydrogen to NH3 to create NH4 plus, leaving the OH minus. This is what's creating the base. Okay, so as you can see, if you have an acid to start, that's going to turn into what we call the conjugate base. If you have a base to start, that's going to turn into your conjugate acid. Okay, so they match up together. All right, so if we look at another one here, we have got HCl and NH3, again, starts with an H, making it an acid. So that's going to transfer over to NH3, creating NH4, leaving Cl minus. Okay, so this is a sort of a neutralization reaction, but that makes HCl the acid, NH3 the base, and then you've got their conjugate pairs on the other side. Remember, if it's an acid on the front half in the reactants, it's going to be a base in the back half or in the products. Okay, again, another example, HNO3 starts with an H. It's going to donate that to SO4 2 minus to create H2SO4, leaving NO3. Okay, so you've got, again, SO4 2 minus being the base, it turns into an acid. HNO3 being the acid, it turns into a base. Okay, so again, here are the pairs that you're going to see. If you're going to have a strong acid, you're going to produce a weak base. If you have a weak acid, you're going to produce a strong base, and so forth, because of the transfer of the ions. All right. We also want to keep in mind that sometimes things have more than one ion. So you can have monoprotic or what we call polyprotic acids. Monoprotic acids are just when they have one proton to donate, something like HI or HCl or HBr or HF, okay? Polyprotic is when they have more than one, like H2SO4, H2CO3. These are only able to donate one proton at a time, meaning that the reaction is going to take several steps. I'm going to show you an example on the next slide. Okay, so if we have something like H2SO4, in this first thing here, H2SO4 is going to donate a hydrogen ion to water, producing H3O plus and HSO4 minus, but we still haven't fully ionized all of those hydrogens, so we've got to start again. So it's a two-step process, because then in the second part, this H2SO4 again donates its hydrogen to a new water molecule, okay, to produce H3O plus again and SO4 2 minus. Now, you can tell here, this is a one-way arrow, this is a double arrow. This is a strong acid here, whereas this is a weak acid down here. Okay, so again, it's happening in several steps. The first step, you can't go backwards. The second step can go backwards and forward. Okay, so if we label our conjugate pairs, again, because here they're donating this hydrogen, this becomes the acid, this becomes the base, this becomes your conjugate acid, this becomes your conjugate base, because if I were to reverse the reaction, this HSO4 minus would be taking a hydrogen ion from the H3O plus. Down here, again, HSO4 is going to be the acid because it's donating to water, which is a new water molecule, which is the base, creating again a conjugate acid and a conjugate base. So if you look here, HSO4 minus is labeled as a base and an acid, making it what we call amphoteric. Amphoteric meaning that you can be an acid or a base. This happens with water all the time, okay? But it you don't see it as often with other things unless they're a polyprotic acid. Okay, and our last example here, again, H2CO3, this is going to be your acid, water is going to be your base because we're going to donate, getting a conjugate acid and a conjugate base. Okay, again, HCO3 minus, donating, making it the acid, water becoming the base, conjugate acid, conjugate base, HCO3 minus is amphoteric.